Okay, let's dive right into this. Welcome to our explainer, baking soda vs powder. So if you're joining us today, there's a very good chance you've, at some point, completely ruined a perfectly good batch of cookies by mixing up two practically identical white powders in your pantry. Right? I mean, we've all been there, staring at those little containers, just wondering why one gives you these beautiful, light, fluffy cakes and the other, well, the other leaves behind this dense, metallic-tasting brick. It's the worst. So today, we are going to finally clear up this confusion once and for all.
Here is our roadmap for today. We're going to cover the appearance illusion, the core chemical difference, the dependency rule, how recipes choose, and finally, thinking like a baker. Let's get to it.
All right, kicking things off with Section 1, the appearance illusion, and honestly, why they look so darn similar. And this brilliantly illustrates the core issue. Imagine you're walking through two stalls in a vibrant Lahore food market. One vendor is selling just a single raw spice, right? It's just one specific ingredient that you literally have to take home and mix with a bunch of other things to actually make a meal. But the vendor right next to them, they're selling a complete self-contained spice mix, where all the complementary flavors are already perfectly blended together for you. Now, from a distance, they both just look like bowls of powder. But dig a little deeper, and you realize one has a single isolated purpose, while the other is a carefully packaged system built to work entirely on its own.
Which brings us perfectly to Section 2, the core chemical difference. Time to look under the hood.
Let's tackle baking soda first. So baking soda is just a single alkaline compound. Chemically, it's known as sodium bicarbonate. It really only has one job. But the catch is, it's entirely dependent on its environment. You can think of baking soda kind of like a single worker in a kitchen who's totally ready to work, but is just standing there waiting for a specific assignment. Or, even better, think of it like a match. A match has a super clear purpose, right? It holds the potential for fire. But it absolutely 100% requires the friction of a strike pad to actually ignite. Baking soda is exactly the same way. It desperately needs contact with an acidic partner to trigger its reaction and actually produce carbon dioxide gas. Now, what's really interesting about this slide is how baking powder completely contrasts with that. Baking powder is basically a ready-made emergency kit. It actually contains three distinct parts. It has baking soda right there in the mix, but it also includes built-in acidic ingredients and a starch. And that starch is absolutely crucial. It acts as a buffer. It keeps the active parts separated and stable so they don't just react prematurely from, the ambient moisture in the air. So the necessary partners, they're already inside the container, just sitting there waiting for moisture and heat to activate the whole shebang. To put it simply, think of it like making a cup of tea. Loose tea leaves are your baking soda. They're a single component, and you have to supply the hot water, the milk, the sugar to actually get the final drink. Instant tea mix, on the other hand, that's your baking powder. Everything you need for the final result is already bundled together. You just add water, and bam, the system activates itself. All right, moving right along to Section 3, the dependency rule. We're talking about the lock and key mechanism here.
So, the crucial point is really this one pivot question right here. Does this ingredient need outside help to do its job? Seriously, I want you to stop and ask yourself this every single time you bake. This single question is literally the most important distinction in our entire explainer today.
Let's actually look at how that dependency translates to real-world recipe behavior. As we see here, baking soda is a single alkaline compound. It needs an acid, something like buttermilk or lemon juice, to react. And when it gets triggered, it releases gas. Baking powder, though, is a mixture. It only needs moisture and heat to produce gas from the acid it already carries inside its own mix. Basically, if a batter has absolutely no built-in acid of its own, baking soda is just going to sit there uselessly while baking powder takes care of business.
And hey, while we're clearing things up, let's just correct a massive misconception. People always say these ingredients make things rise. But honestly, that's kind of skipping the actual mechanism. What they really do is produce gas. Think of air being pumped into a bicycle tire. The tire doesn't get bigger because of some magical rising property, right? It gets bigger because trapped gas bubbles are taking up space and literally pushing the mixture outward. And that is exactly what is happening inside your cake batter.
Which perfectly tees up Section 4, how recipes choose. It's all about reading the environment.
Let's move to the environment your recipe actually provides and see how this builds. If your recipe already has enough acidic ingredients, we're talking yogurt, buttermilk, vinegar, or, even brown sugar, then baking soda is your better fit. The soda will react directly and very quickly with that existing acid. But if the recipe has little to no acid, baking powder is the hero because, remember, it brings its own.
And interestingly, this is a cool little trick. If you need extra browning on a cookie, baking soda is often the go-to because it raises the alkalinity, which actually encourages a much deeper, darker bake.
But I really want to challenge you here for a second. When we look at leaveners, will it rise is pretty much the only question people ask. We just naturally assume that getting some lift is the only thing we're trying to achieve. But is that really the whole story? Not even close.
Because beyond just rising, these chemical reactions fundamentally alter your final product. For instance, if you use baking soda without enough acid to actually trigger it, you're going to be left with this terrible, soapy, metallic taste. It's gross. And as we just saw, alkalinity changes browning and color. Plus, the speed of the gas bubbles forming completely dictates your crumb texture, whether it's super airy, dense, or perfectly crisp. And timing? Timing is everything. If your gas escapes way too early before the oven heat can set the batter, your entire cake will just collapse. You are literally balancing an entire delicate ecosystem in that mixing bowl.
And that brings us right to our final section, thinking like a baker, diagnosing the batter.
Look, if you write down only one thing from this entire explainer today, please make it this exact sentence. Baking soda asks the recipe for acid. Baking powder brings the acid with it. I mean it. This is the ultimate takeaway. This single sentence unlocks just an incredible amount of baking science. It explains your kitchen failures, it explains your successes, and it even explains why some recipes actually call for both.
You've officially made the shift from simple recognition to deep reasoning. You're no longer just guessing when you rummage through your pantry. You understand the timing, the dependencies, and the underlying chemical reactions that are just waiting to happen. So the next time you look at a bowl of generic white powder, ask yourself, what invisible chemical system are you about to trigger? Thanks for hanging out with us for this explainer, and we'll catch you next time.